Okay, so let's start. It's my great pleasure to have today Mariagrazia. She's from Politecnico di Bari in Italy, and we collaborate since many years in the context of System and Cybernetic Society. We are both in the BOG, in the Board of Governors, and we also organized several joint events together. Okay, so I kindly remind you that this is the virtual lecture series of our chapter, the Italy chapter of the System and Cybernetic Society. Today the lecture will be, in my opinion, very interesting, because we will have an interesting topic related to COVID-19 from one side, and from the other side, Mariagrazia is an excellent researcher. She's currently full professor at the Università Politecnico of Bari, Politecnico di Bari. If you'd like to translate, University Politecnico of Bari, okay, in the South Italy, from Puglia in the South Italy. And she is a full professor of systems and control engineering. She's also currently coordinator of the PhD program at her university. She holds a PhD from the same university, and she had many different experience abroad, in France, in Denmark. She published extensively more than 200 scientific papers, and her main research topics are related to modeling, identification, management, control, automation, optimization of discrete-event industrial systems, manufacturing systems, and so forth. As I told you at the very beginning, Mariagrazia is very active in IEEE, specifically System and Cybernetic Society, but not only in this society, also in the Control System Society. She was the editor-in-chief of the e-newsletter of our SMC Society, and currently she's a general chair of MED 2021 that will be held in the Bari area, hopefully in presence, because you know the Bari area is very nice. Puglia is very nice. Otherwise, of course, the event will be hybrid one, so partially physical and partially virtual. So please, Mariagrazia, share your screen. And again, pretty glad to have you here, and go ahead with your presentation. Thanks a lot.
Thank you, Giancarlo, for inviting me today. It's my honor to be here, and welcome everybody. Can you see my slides?
Yes, please.
Okay. Thank you also for your kind presentation. And I take this occasion also to invite you all to Bari for the conference. Actually, the 1st of March is the deadline that is still open for presentation-only papers. Okay, so thank you again. I would like to mention that the work that I will present today is a joint work from my lab. In particular, first of all, I would like to mention Paolo Scarabaggio, who is also connected. He is one of my PhD students. He's doing a brilliant job in this area. And also the research associates of my lab, in particular, Raffaele Carli, Graziana Cavone, and Nicola Epicoco. Can you see my second slide now?
Yes, yes.
Okay, so this is the outline of my presentation. I will briefly present my group and then the motivations and objectives for this work. then I will position it in literature, in the related literature, and I will start. I will try to keep the presentation simple. Of course, I'm a control engineer, so my main interest is modeling and control, but I would like this presentation to be useful for everybody, not also control engineers, of course. So I will start from mathematical models that are used for infectious diseases, and then I will present the CQT model that my group has developed specifically for COVID-19. I will deal a bit about parameters identification because this is an important issue with all these infectious diseases models. And then I will talk about how we can control these diseases. So this is again our specialty. And in particular, we'll refer to controlling the COVID-19 outbreak. And then Paolo Scarabaggio will present some numerical experiments and I will draw the conclusions. So this is my group. Here on the bottom, you can see the link of the web page of our lab. And from that web page, you can also go to a dashboard on COVID-19 where there are many information on this topic. And also, I would like to mention that the slides of this presentation will be made available, if not already, on this channel of Teams. This is my group, and together we are working, as I mentioned, basically on decision and control. In fact, the lab is called the Decision and Control Laboratory. We work in particular in theory and applications on decision and control of complex systems, I would say, with a special interest on technology transfer, research and technology transfer. And currently, since a decade, I would say, we are working in particular on complex dynamical systems, both from a centralized but also decentralized and distributed way. And lastly, in the last year, we focused a lot our attention on the COVID-19 disease that unfortunately has affected the whole world. Here you can find some of our collaborations. I will now go to describing the motivations and objectives of the talk today. As we all know, since for a year, basically now, the SARS-CoV-2 coronavirus disease has caused more than 2.5 million deaths worldwide and 110 million of confirmed cases. And actually, these numbers are growing continuously. And so this is basically the most impacting pandemic in the recent decades. Of course, vaccinations are very important issues, but however, they are still being developed. So we have not arrived yet, unfortunately, to reaching herd immunity. So until that, and until we find a good way to cure, so good medications to cure COVID-19, what we can do is, in fact, rely on control. So what are the main control actions we can rely on? They are basically non-pharmaceutical interventions, so basically mobility restrictions and social distancing. And so the work that we present today is motivated by the emerging need for developing effective methods to support policymakers, possibly in an automatic way, in efficiently mitigating the effects of COVID-19 pandemic contagions and taking the decisions in this field. It is important to remark, of course, that the related literature in the last year is rich of contributions, evidently, because of the interest for the whole global community in this subject. And the recent research threads in COVID-19 have been devoted basically to studying modeling and control with the aim of suppressing or at least mitigating the spread of the infection. Indeed, there are many different models that are available in the literature to describe the COVID-19 dynamics, and you can refer to the paper from Zhao and Chen for a discussion on those. In the slides at the end, you will find all the references that you can study if you're interested in subject, in deepening your knowledge on the subject. Some works focus on the analysis of the pandemic at a regional level, which I find very important, because these works allow to take into account the economic and social differences that exist basically in almost any country. I'm talking about Italy here, but even in any big country like China or US, of course, you find many differences if you change area or region. However, most papers generally lack an accurate identification of the pandemic's dynamical model parameters. Regarding control, very very few models are presented in a related literature to investigate the effects of control strategies. The few models that are presented, they are very simplistic. They use basically what-if simulations of future scenarios to make decisions. In addition, most of these models do not provide a feedback control method to properly identify and choose the most effective mitigation actions and employ them in a dynamical framework. What has been done by some authors is to propose some open loop on of social distancing measures or fast switching policies. In addition, in most of the published papers, a perfect knowledge of parameters is assumed, thus ignoring uncertainty, which, however, characterizes this phenomena. I also want to remark that the optimal control theory has been already successfully applied to identify the best action strategies for other diseases. So what is our contribution? We are presenting a novel time-varying epidemiological model that is designed in order to allow a robust parameters identification. So the first contribution is basically on the model, but then the second contribution is on the control of the pandemic. So the model leverages the mobility of people in different socioeconomic categories to represent the time dependency of the infection rate. And based on the model, basically we propose a control approach that uses model predictive control that allows avoiding the healthcare system to be overloaded. We also are able to take into account the economic impacts of the design control strategies, and we include uncertainty on the parameters in the model. And finally, our approach is able to model the pandemic in a diversified multi-region scenario. So it's able to take into account diversity in different regional zones of the considered system. I also would like to mention that the results presented in this talk have been published in a paper published in Annual Reviews in Control last year. And we have already two other papers that are submitted, one on the transactions on the automation science and engineering, and the other one at the conference that will be held in Bari. So let us start very simply talking about the main compartmental models in epidemic modeling. The first mathematical model that was proposed for infectious diseases was formulated by Kermack and McKendrick almost a century ago. Today, compartmental models are widely used to model the dynamics of infectious diseases. Basically, in these models, the population is divided into classes that are called compartments, and people may flow between these classes with characteristic rates. The models are either continuous, so using ordinary differential equations, or discrete, so using finite difference equations. They can also be defined in a deterministic framework or in a stochastic framework, and of course the stochastic ones are more complex. So let's start from the simplest model existing in this area, in particular the SI model. The susceptible infectious model is very useful for single wave epidemics where infectious people cannot be healed. So an example is HIV. Basically, we have two compartments, S and I, the compartment of susceptible individuals and that of infectious individuals. And susceptible people simply can move to be infectious with a certain rate. So if we call N the total population size and beta the infection rate, basically we have that the variation of the infectious people over T is simply can be simply expressed as beta, which is the infection rate, multiplied by the product of the infectious individuals at the time instant, multiplied by the number of susceptible individuals, divided by the overall number of population. And then, of course, since there is a conservation of mass, we can represent the variation of S over T, so of the susceptible numbers of individuals, in the same way, just putting in the same analogous equation with a minus. However, sorry, note that in these classes of model, typically a main assumption is that the population is constant. So we have N equal to S plus I. And this makes sense because the time constants of this kind of modeling are faster than other time constants. So for example, births and deaths. And so this is why we can simply substitute to the value of S, so the susceptible individuals, simply N minus I. And so we get an equation, single equation with respect to the variation of I over t. So we get simply a nonlinear model of the first order, so represented by a first order differential equation. It is nonlinear because we have the square here of I, and this can be actually solved in closed form, and this is the solution that we get. Of course, the solution will depend on the size of the population, on the initial number of infected individuals, I of 0, and it will depend on beta, which I remind you is here. Beta is the infection rate, which is a very important parameter. It is also easy to prove that this model has two equilibrium points. The first equilibrium point is the disease extinction, and this is unfortunately unstable. And the second equilibrium point, which is unfortunately asymptotically stable, which corresponds to a fully infected population. So this is an example of what happens to the dynamics of the infectious people over time. On the x-axis, we have the time units, and these can be seconds, months, or even years, depending on the dimension of beta, because beta is basically a frequency. And so this depends really on the incubation time of the disease. So for example, for beta equal to 0.3 and a population of 1,000 individuals, we start from just one infectious individual, and after about 40 time units, we arrive to a population that is fully infected. Of course, the dynamics changes. If beta is bigger, clearly the dynamics becomes faster. Of course, this model is very simplistic, and so an initial model that can be defined that is more interesting is the so-called SIS model. In this case, we assume that a part of the population that has been infected, so that becomes infectious, that is in the class I, can actually go back to being susceptible. And this is defined by a so-called recovery rate gamma. So in this case, in the equation of I, of course, of the variation of I, of course, we can add a term that is negative, representing the fact that there is a flow of individuals that go back from I to S. And again, keeping in mind that n equal S plus I, we simply obtain the following equation. So we have an equation that is similar to the original one that we had for the SI model. It's still a first order nonlinear equation, only in this case we have added this term minus gamma I. Also, this one has an analytic solution in closed form, and basically the difference here is that the results depend on not only on beta, but on beta minus gamma. And again, the model has two equilibrium points, the extinction of the disease and an asymptotically stable equilibrium, which is interesting to notice that depends on beta minus gamma over beta multiplied by n. So again, the results will depend on these values, beta, gamma, and n. And so what happens basically in these dynamics is that the dynamics tends to a so-called capacity of the population. So over time, what happens is that not all the population gets infected because there is this going back from I to S, but a part of the population becomes infectious. And here, of course, this number depends from beta and gamma. So here you have a representation of what happens when beta is equal to 0.3 and gamma 0.1. And of course, the curve changes, for example, if the difference between beta and gamma is higher. We can still modify this model by using the SIR model, which is probably the most famous model for infectious diseases. And this is very useful, again, for single wave epidemics where you have natural immunity. This model has been used already to model measles, mumps, and rubella. And for the Italians that are connected, I would like to remember that measles is morbillo, mumps is parotite, and rubella is rosolia. So basically, in this model, what happens is that susceptible individuals, again, can become infectious, but infectious individuals can be removed. So we have a removing rate gamma that leads the individuals to a new class of people, of individuals. Again, we have that n is equal to S plus I plus R. So the equation of the variation of I of the infectious individuals is similar, actually is the same as for the SIS model, but here we have three state variables, as we call them in control systems engineering, which means that by using the equation on N, we can eliminate one of those, and so we obtain a system that is a second order system. However, we cannot solve the equations that we obtain analytically in closed form as in the previous cases, but we may solve numerically the equations using an engineering computation software. It can also be found that there are an infinite number of equilibrium points that are all characterized by the fact that I is equal to 0, R is a constant, and S, of course, is the difference between the population dimension, and the value of R. So what we can do is for fixed parameters, so knowing beta and gamma, we can solve numerically the system equations and determine the final epidemic size, that is the values S and R, when time tends to infinity. So it is interesting to remark that the behavior of this pandemic curve, so of the susceptible number of individuals infectious and removed, change completely, again, depending, of course, on beta, on gamma, on the dimension of the population, and on the initial values of the number of individuals in the three compartments of classes. So see, this is what happens when we have only one infectious individuals at the initial time. And this is, you can see that here there is a peak, and we have all seen all those peaks recently, unfortunately, on our TV news. So we are very much focusing on this. So this is another example of what happens when beta, for example, is higher than before. The peak gets higher, and also, unfortunately, you get it sooner. But it also becomes, let's say, less large, so it's more contained. So a question arises immediately, and we all know by now the answer of this, again, by following the TV news. So the question is, how can we simply evaluate an epidemic? And the answer is an easy way to evaluate an epidemic is to compute the basic reproduction number R0. The basic reproduction number R0 is simply the number of secondary infections that a single infected person would produce in a fully susceptible population through the entire duration of the infectious period. So I'm considering a fictitious, evidently, case in which the population is totally in the susceptible compartment, except for one individual which is infectious, and I want to compute the number of secondary infections that the single infected person would produce. This number is called R0, and it provides a threshold condition for the system dynamical behavior. It can be demonstrated, it has been demonstrated in the literature, that if R0 is smaller than 1, basically we are not in the case of an epidemic. And what happens is that the number of infectious individuals decreases monotonically to 0. So the disease basically is cured by itself. On the other hand, if R0 is bigger than 1, then we are in the case of an epidemic. We have a peak in the number of infectious individuals before, again, a reduction to 0. It is interesting to remark that R0 can be simply defined as the ratio between beta and gamma. And for COVID-19, the basic reproduction number R0 is estimated between 2 and 6. In the case, of course, of no restrictions. Here you see in this figure here the R0s for different diseases. For example, it's interesting to notice that for measles, R0 is very high, it's 18. For HIV is 4, and for hepatitis is 2. And so going back to the previous kind of graphs, here we have what happens when beta is equal to 0.3 and gamma is 0.1, and we start from a higher number of infectious individual, in particular 100 infection individual. In the case, R0 is equal to 3. You see a peak here, so there's clearly a pandemic. And instead, when the ratio between beta and gamma becomes becomes smaller than 1, for example 0.5 in the case because gamma, the removal rate, is much higher, you see that the number of infectious individuals, the red curves, goes to 0 basically spontaneously without a peak and without many problems for the population. So an immediate question arises for this case. How can we control an epidemic? Of course, the first answer is to reduce S, the number of individuals that are susceptible to the disease. And this can be done by reaching herd immunity by vaccination. Unfortunately, for COVID-19, we are not yet there. So this is clearly the most important way to control the epidemic, but we're not there yet, and we hope that we will be there soon. So not being able to do that, what we can do, what we have been doing basically for the last year, we can reduce beta. Beta is the infection rate. How can we do that? By washing hands, by isolating sick persons, by shutting down public events, by closing schools, and so on. In this way, we enforce the decrease of R0 over time and try to make sure that R0 becomes smaller than 1. What we can also do is to increase gamma, so the removal constant. However, this can be done basically by having better and faster clinical treatments or antivirals. And this, again, we are doing something on this worldwide, I mean, but still we are not there, basically. So the main my main point in this presentation is that at the moment, from a control point of view, we are basically left to consider the second type of action. So we have to reduce beta. Here also you have the representation in this figure of R0 in the first month and a half, 2 months of the pandemic. When we had lockdown basically everywhere in the world for some countries like the UK, the US, Italy, and so on. And you see that the lockdown actually worked because R0 went down to 1, starting from much higher values in the autonomous case. So in the case of no restrictions from the beginning, where R0 was, again, as mentioned, between 2 and 4. Of course, this SIR model can be modified in many different ways. We can model the dynamics of births and deaths, but this is often neglected because, as I mentioned, the time constants are of this kind of epidemic are much smaller. We can include time varying parameters to take into account the effects of seasonality and control policies. We may divide the population into more groups. We may include additional compartments for vaccinated, and we are actually studying this. We can model heterogeneity in age, regions, or host species. And as I mentioned, we're working especially on regions. So there is a number of epidemic models, and basically you can divide them into classes: single epidemic waves and models that study the endemic equilibrium, so the situation in which the disease cannot be totally eradicated but remains in the population. And again, I leave you to the surveys that we have put in this presentation at the end of the presentation if you're interested in this. So what did we do in our group? We tried to develop a new model that we call the CirQT model. First, we modeled it for a single region or nation or area, and then we generalized it for several different regions. In particular, the model that we proposed is a time-varying, discrete time epidemiological model, and the overall population is divided into 8 compartments. So we have, again, the susceptible ones. We have the infected individuals. This means that are individuals that have been infected but are not yet contagious, so they are at the beginning. And of course, after being infected, you can have individuals that are removed, so they are not detected by, for example, the national authorities, but they are simply completely recovered by themselves. Others, they become contagious, so they are not only infected and undetected, but they are contagious for other people. Some of these are detected and unquarantined, so these are infected and detected. There are also threatened individuals that are basically hospitalized, and this category can also be divided into 2 categories. So people that are in a life-threatening situation and others that are in non-critical situations. And then, of course, we can have two terminal compartments, as we call them, the healed compartments, but of course we can have also the compartment of the extinct people, so people that are dead and detected, meaning that the national authorities detect their death because of the pandemic. It is also important to notice that we reasonably assume that the probability of becoming susceptible after being healed is neglectable. It is, of course, non-zero, but since the dynamics is much slower than the actual mean time constant of the model, we neglect this. So this is basically the scheme of the flows of individuals between the various compartments. So from susceptible, an individual can become infected. From being infected, either it stays infected or it becomes contagious. From contagious, either it becomes removed or it is detected and quarantined if the situation is not problematic or threatened. And of course, there are flows in between quarantine and threatened cases. And luckily, there are healed individuals, but of course, before being healed, when you are hospitalized, so threatened, you have to be quarantined. Otherwise, unfortunately, there are also cases in which the threatened people die, so they go to the extinct class or compartment of individuals. What you see here is basically the in all these links is basically the representation of the quantities of people that are flowing from susceptible to infected, leading to exactly 8 state equations. In particular, as I mentioned, they are differential different state equations. So the system is discrete, as I mentioned. And since we have 8 state equations, the system is of the 8th order. Of course, there are many nonlinearities. I would not go into detail in this on these equations because you will find them in the paper that I mentioned before. But basically, the nonlinearities are due to the products that you find here in the case of contagious multiplied by susceptible individuals, exactly as in the seminal work by Kermack and McHenrick. So these are the main nonlinearities. However, there is also the fact that this model is time varying. Because not all coefficients are constant. In particular, beta is not constant over time. And this is, of course, because of the fact that we apply some mitigation strategies, so some control actions, like, for example, lockdown or closing schools or reducing transportation and so on. And also the epsilon, so the rate of death actually is not constant, but it depends on the situations in the hospital, so on the number of threatened people, because if we have hospitals that are really full and that cannot take more patients, clearly people unfortunately tend to die. I also would like to mention that the symbol tilde identifies the state variables, so the compartments whose numbers cannot be directly observed from information from the national authorities with a reasonable confidence, since no official data is available. And these are unfortunately the susceptible, the infectious, the removed, and the contagious people, while we have data on the gray compartments here, so on quarantine, threatened, healed, and extinct. However, in order to correctly represent the spread in a multi-region area, exactly like we have, for example, in Italy, where we have 20 regions, and we know that there are very different situations. For example, if you consider Lombardy, or for example, if you consider Valle d'Aosta, where the situation is much less critical, we also generalize our CQT model to a case with M different regions. This means that we have to rewrite the previous 8 equations for the M regions. So we have a number of M multiplied by 8 equations. So the system, of course, becomes much bigger. But also we have to model the fact that there can be mobility between regions, and this mobility is represented in the two compartments that can move, and these compartments are basically the susceptible and the contagious one. So if we consider these two equations here, we can add some terms, so these two summations that we have here, that take into account the migration of individuals between regions. In particular, we use the time vary coefficient zeta ij, where I and j are the two regions between which we have the mobility, to represent the interregion mobility that affects the two equations. Of course, there are some conditions on these indices. In particular, the summation of all these indices of all these flows has to be zero, because the population is kept in the whole system. And we also assume that all parameters are positive except those that represent the mobility in the region, in the single region. So people that do not move, basically, that do not go to other region. And this is represented by zeta ii, which of course is computed as minus the summation of all the other parameters, of all the other flows to that ith region from all the other jth region. What are the advantages of our model? There are several advantages. We tried to keep the model simple, so we compressed or eliminated some classes, but still we wanted to ensure a good accuracy in the fitting phase. And indeed, despite the simplification, our model is still able to represent all facets of the pandemic diffusion. The model employs two terminal compartments whose characteristic parameters are easy to calculate. It only requires a minimal set of epidemiological data that are all known, so those on the four compartments that I mentioned. In particular, the infection rate is assumed time varying since it depends on the population behavior. The death rate is modeled as a function depending on the threatened people. And last but not least, the model has a broad applicability when it is considered in its multi-region version. About parameters identification, this is a very important issue, as I mentioned at the beginning, and I will refer to Italy to fix ideas, but of course all this can be generalized to any country worldwide with this model. As we know, in particular, after the exponential growth of cases in November, the start of November last year, the 20 Italian regions have been grouped into different epidemiological categories based on the monitoring of a number of indicators. And basically what is happening still now in Italy is that the regions are divided with four colors: white, yellow, orange, and red. White means that the contagion is minimal, so no control actions are enforced. When the color becomes more dense, so it becomes red, we are in the case of serious contagion and maximal control actions, and other intermediate situations in between. How is this done? As I mentioned earlier, basically they take into account in the control action the infection rate beta of k. In particular, we employ the Italian Civil Protection Department epidemiological data, so the data of the Protezione Civile, that gives us the information on the threatened, on the quarantine, healed, and extinct or deceased people, so T, Q, H, and E. And we also know from Protezione Civile the swaps number that we call W of K. The problem with this data is that they are daily data and they only represent a screenshot every day of the epidemiological situation. In other words, we don't have a representation of the flow of individuals from one compartment to the other every day. So we don't have an information from Protezione Civile regarding on the dynamics between the different compartments. So some assumptions must be made to compute the various parameters, so the various critical rates, characteristic rates, beta, gamma, epsilon, and so on. And that's what we did. This is the most important assumption that we did. We observed from the related literature that the value of the infection rate beta is usually assumed between 0.25 and 0.8 in the absence of any social distancing policies and people awareness. So when the system, as we say in control, when the system is autonomous, there's no control. But of course, if you apply social distancing or restrictions or even lockdown, beta can be reduced very significantly. So to assume, to achieve a fitting of the dynamics, we assume that the variation of beta is related to the evolution of people's mobility in different socioeconomic categories. So we assume that we can define G different socioeconomic categories, and therefore the infection rate may be defined by this equation here, by this simple linear equation here. Beta of k is simply a nominal value plus the scalar product of beta transposed multiplied by m of k, where beta collects the infection rates corresponding to the G categories, and m of k collects the so-called mobility levels in the 0-1 range for the different categories. So this means that when m is 0, there's no mobility. When m is 1, we have the maximum mobilities. And in general, these levels assume a number in the range 0-1, so in between, depending on how big are the restrictions. Of course, if I have the maximum restriction, total lockdown, clearly m is equal to 0. How can we estimate these numbers? We can estimate them very easily in considering the Google Mobility Reports that represents these data in several categories. In particular, to simplify things, we chose the following 3 mobility categories: workplaces, retail, and public transport. And here on the right, you can see the representation of these mobility levels in the various Italian regions. And you can also note the peak, for example, that we had in November for mobility, because in November there was the decree of the Prime Minister, the first important decree of the Prime Minister, the DPCM of November 6, that reduced immediately very strongly mobility and caused again the changes in color. So for example, some region became red, as Lombardy, Piedmont, and so on. So we can also determine the incubation rate as a constant, and this is estimated basically by information from the literature and the fitting algorithm that I will describe in a moment. Also, hospitalization rates and the rate ME from quarantine to threatened can be defined as constant. The healing rate gamma from contagious to remove is also obtained as a constant by information from the literature. And the removal rate delta can be approximated by a constant value. This is shown by a number of examples. It is also important to notice that delta can actually be obtained by simply solving backwards the equation on the healed people, because we have information from the national authorities regarding the healed people and the quarantine people. So if we have information from the past, we can observe delta and have these numbers. And really what we get is that delta is basically a constant. Now, the most critical parameter in all the model is the detection rate theta. So the fact that we detect people that from contagious have to be quarantined. And this is obvious because, of course, when people is really in a difficult condition, this is clearly detected, we call an ambulance, and people are sent to the hospital. What is much more difficult is to understand this theta parameter, so the parameter regarding the flows from contagious to quarantine. And this can be done by using the ratio R between the new daily discovered cases P and the daily swabs W that we know from, in the case of Italy, from Protezione Civile. What happens is that when this ratio R increases, clearly the pandemic is out of control and the tracking system is not working well. However, conversely, when R is low, the pandemic is under control. And what we define, and this is also an important assumption and innovation of our work, is that theta of k can be defined as a linear relation with R of k. So with this ratio between P and W. And again, note that to the best of our knowledge, no other approach in the related literature assumes theta to be time varying, but typically this is simplistically chosen to be constant and causes inefficiencies, of course, in the models that are used. Then we can define the recovery rate. And here we have to distinguish between the first stage of the pandemic, in which really the situation in the hospital was totally chaotic. And so what could be done was simply to define pi, the recovery rate, using a fitting function. Luckily, now in the second stage of the pandemic, pi can be considered constant, meaning that really the situation is no more in chaos any longer. Here are the data of pi for the first stage of the COVID-19 pandemic. In blue, you have the output of our model, and in red, you have the actual data for all the different regions in Italy. And again, you see that there are some regions in which the model works better, others less, also because some regions, for example, if you see Molise, they have a much lower number of people, so the population is much lower than in other regions, and so it's more difficult, of course, to fit the model. Another important element is the death rate that can be determined similarly to delta and pi, so I will skip this. And here are the results of the model for the first stage of the pandemic. And for the second stage of the pandemic, considering the linearity of epsilon. Oh, I forgot this. This is important. Sorry. We basically assume that epsilon, the death rate, can be considered linear with the threatened cases, with the number of people that are hospitalized. And this was not true for the first part of the pandemic, again, because there was chaos in the hospitals. But now that the hospitals are dealing much better with the cases and that the disease is much better known, you see that the identification of the parameter is much easier. Again, Molise is a region in which data are not so linear, also Campania, but mainly the model works very well. We then define an identification of the parameters using a least square optimization techniques and a fitting algorithm. Since we are late, because it's already almost 10 to 1, I will totally skip this part. I'm sorry. This is actually a very important part, but you can find it in the slides. So basically, we used, as I said, the mean squared error technique to find the better fitting values of the various parameters. So you can read the slides, and these are just the results. These are for simulations made from September to December, again in Italy. So you see that the parameters are fitted very, very well, such that the four state variables that can be observed, so the quarantine, threatened, healed, and extinct numbers, are perfectly evaluated, perfectly foreseen by the model. You see in red the actual data, and in blue the data that we determine with our model. So this is for the quarantine case, the threatened cases, the healed cases, and the deaths. And you see that the model works perfectly well. I will skip again the dynamic identification of the model parameters. Please have a look at that. I would just mention that we do a observation of the last 3 weeks for the fitting window, and we generate a forecast of the system variables over a forecasting period of 1 month. In other words, we evaluate the situation, the future dynamic of the system, by considering the parameters for the most recent data, so the last 3 weeks, the mobility trends from Google, and we determine the future control actions in terms of mobility reductions, and finally, we determine the age set variable. So I will leave the floor for a while to Paolo Scarabaggio, who is one of the co-authors of this paper. Paolo, are you there?
Yes, I'm here. So hi to everyone. I'm Paolo Scarabaggio, as presented by the professor. I would like to introduce what we have done during the last year with the Decision and Control Lab, mainly for monitoring this pandemic. We started really early, since March 2020, with a really small dashboard that is based on the model presented by Professor at the beginning of this talk. This model basically showed the data, real data from civil protection, as showed only 2 charts, one for the total cases and another one for the daily new cases. As you can see, the cases were indicated with histograms, the one of the official number, And in yellow, we showed our forecasting. As you can see, the fitting was quite good. We stopped this model in May, since there were no new daily cases, so there were no needs to use this model. Professor, can you go to next?
Yes.
Yeah. We showed also results on a really local basis, as we show the 6 provinces that compose our regions. Of course, here the data are affected by statistical error, since the number are smaller, but the model still worked in a sufficient good way. Next slide. Now I want to mention that we keep working on this model, and we came up with a model presented by Professor that is now currently running on our website, and you can find a really interesting dashboard at this link, where we showed results that we made employing, as said by Professor, using a fitting horizon of 3 weeks, so taking the past data of 3 weeks and making forecasting for the subsequent 4 weeks. Of course, these data are based on mobility data. We showed also all the data, all prevision to show the model accuracy, and we have, of course, quarantined, healed, threatened, and dead people. Of course, dead people and healed people are much more fitted in a better way, since their data are more accurate. Next slide. I want to mention now this that can be seen as an error of the model, but it is not an error, since with a dashed line you can see the forecasting made 3 weeks, 2 weeks, and 1 week before, and with the continuous line you can see the real data. This is not an error because our model works with mobility data. So it takes the trends of employing the mobility reports. So in the 6th of November, the government imposed new restrictions that were suddenly applied. So our model was not able to detect it if not manually included in the model. And so it has this small problem that shows basically that the number of hospitalized people was going to be closer to the 75% of the overall bed capacity in our regions. But then the model worked well for the next month. And on the website you can find also other data, mainly take from Oxford University, Civil Protection Department, and John Hopkins University. I give back the...
Thank you very much, Paolo. Now, a few words. We don't have much time, but I think this is the most important part of the presentation. A few words on control. So we assume that the mitigation strategies are focused on reducing the parameter beta, so the infection rate, as I mentioned earlier, such that on the long term, even in the absence of vaccinations, we are able to reach herd immunity. How can we get that? Of course, we have to use the mobility of people, which is exactly what the various governments are doing, and our assumptions are confirmed by several works. So the mitigation strategy should also ensure that the hospitalization capacity is not violated and that economic losses are minimized. So we define an optimal control problem where the optimal control policy U is assigned over a control horizon of K time steps, where H indicates the current time step. Of course, the most obvious choice is to have as each time step 1 day, because every day we have new data. So that's the most obvious choice, but it's not necessarily the one, because it depends on how we get the data. So at each time step, we collect the G control actions, so the mitigation strategies for the various socio-economical categories. And I remind you that we chose 3 categories, so workplace, retail and recreation, and finally transportation, and collect the control actions in a vector U, so which is made of G control actions that collects interventions on mobility for all G socioeconomic categories. So we can rewrite the equation of beta that depended on mobility by enforcing mobility through this control action, and so by rewriting the equation as here, where U again is selected into interval 0, 1. We also want to mention that an intervention in one category is not independent from an intervention in another one. So for example, if we intervene as a government on mobility as regards workplace, this affects mobility on transportation and vice versa. Also, in order to avoid too frequent and impractical changes in the strategies, because we are talking of a social model here, the control actions are kept constant for 7 subsequent samples, which means a week if we consider 1 day for every sample. So we also define an objective function using optimal control that we want to minimize. However, the objective function is made of 3 terms. The first term is simply the summation of the control action multiplied by some weights, plus where these weights take into account the economic impact of restrictive measures. On the other hand, we also consider 2 other terms here, which are called regularization term, that allow the first one to smooth the restrictive measures over the control horizon. We cannot have a bang control, like 1 day we close everything, the day after we reopen everything, and then we close because, again, the population needs some time to adjust to control. And the last term here is a memory term that allows to avoid the variation of decisions taken in a previous time step. Again, we want the variations to be smooth, not too strange. Finally, we have alpha 1 and alpha 2, which are weights that are selected by the decision maker in order to decide which of these 3 terms is more important. And vector phi k, as I mentioned, collects the cost coefficients and allows giving a different importance to the different categories. Do I find more important workplaces? Do I find more important as a decision maker, for example, transportation or retail, whatever. Basically, the optimal control problem is defined as minimizing J subject to the model, some constraints on the decision variables, and most important, a constraint that allows to impose that there is a safety threshold on the regional healthcare system capacity. So, for example, I don't want more than 30% of hospital beds to be taken. Very quickly, we redefine this model also for the regional case. So by assuming that our control actions can enforce the flows between 2 different regions, because as a regional governor, I can decide to close all the borders or to open them with the other regions. And so basically the objective function can be redefined as the summation of the single region objective functions. And so this is the most important political questions. How can we select the different control actions, inter-region travel restrictions, so restrictions between regions, and the mobility restriction inside the regions? There are basically 3 policies. First one, everything in the same way. This policy was implemented by the Italian government and by many governments in the first phase of COVID. So we have the same decisions for every region, inside every region, and the same decisions regarding the borders. We can have a differentiated intra-region restrictions, so borders between some region can be opened and some other can be closed. And we can have uniform inter-region travel restrictions. So, for example, all the shops are closed after 6 p.m., all the restaurants are closed at night, and so on. And this policy is currently implemented by the Italian government. So all the regions are applying the same internal decisions. On the other hand, we can also have differentiated intra-region activity and differentiated inter-region travel restrictions. One final word about the model. In the last paper that we are publishing, we are, and this is very important, we are writing the constraint regarding the number of beds in a probabilistic way. This is very important because I can accept as a regional decision maker some risk to go up the threshold that I decided, for example, 30% of beds or 50% of beds or whatever, because there is still the capacity at a national level of beds that I can use. So of course, this makes the problem more complex because it becomes a stochastic optimal control problem in this case. And this is finally the implementation of our model. So we use a model predictive control approach in which the problem is solved at each time step in a rolling horizon manner. So the problem is defined as solved in an iterative way every week. More precisely, the control actions that we compute considering all the knowledge until now for the future are only used for the first time step, so for the next time step, and they are then applied to the system to steer its behavior to the desired one, while the horizon is shifted forward again of one step. And so this is a representation of the system. This is the network of Italian regions from which we get the data, and also, of course, the Google Mobility reports. We define our So we solve basically an optimal control problem or a stochastic optimal control problem subject to several constraints, the most important of which are evidently the model, the circuitry model. And solving this, we get the control actions that we enforce on the system. Now I leave for really a few minutes only to give you a flavor of the results. I leave the floor to Paolo.
So we applied our model for a scenario simulation of 10 weeks, and we employ a prediction horizon for the optimal control problem of 6 weeks. The cost coefficient that we use are based on the ZDP, the regional GDP, and we use the 3 categories as mentioned by Professor. We take data of Tmax by using the Ministry of Health official data. And we set the restriction combination based also on mobility reports. Next slide.
Sorry.
Okay, here you can see the computed set of restrictions for employing the mobility reports for all the regions and for all the color that represent the control actions. And in the next slide, we basically employ, these are only data related to the simulations. We employ a level of risk of 0.2, but of course this can be changed as a decision maker want. And then in the next slide, in this slide, I want to show the results of the optimal control problem. So the results computed by solving the optimization problem over a 6-week simulation. Then here in the dashed line, in the black dashed line, you can see the total number of beds that cannot be overcome. And then we also performed a Monte Carlo simulation starting from our model. Basically, we just changed the model parameters a lot of times, like 1,000 times. This because we wanted to take into account the uncertainty in the model. And then we show this by showing the confidence interval that you can see in Chan in the picture. That, of course, is still under the maximum number of beds in the hospital. I want to remark that only the first step of this control action are applied. In the next slide, this is basically the same results, but for all the Italian regions. And now these are the results for the MPC approach. That is basically the concatenation of all the result or the first step of the results of all the optimal control problem. So we basically run the optimal control problem several times. We took the first result, we applied, and here is the result of all these actions. Of course, to model, we have to model uncertainty, so we introduce like disturbances and noise in the model, like changing the number of cases. I should mention that in this case we use a different Tmax, like and we employ 50% of the total beds capacity. Here you can see a difference between these two pictures because we changed the coefficient alpha 1 and alpha 2 that are the memory terms, the regularization term mentioned by Professor. And you can see, of course, in the first case, the control action is more shifted easily. On the right, you can see when alpha 1 and alpha 2 are equals to 1, the control action is not changed by the optimizer. So this is a matter only of decision maker to select the best. These are all the results for all the Italian regions for alpha 0.1, and this is again for alpha equal to 1.
Thank you, Paolo. So concluding, over the last months, as we all know, unfortunately, COVID-19 has affected the whole world, and we are all waiting for vaccinations and for medications. But while waiting for that, the main mitigation actions of the pandemic only rely on the use of non-pharmaceutical interventions. So these are basically control measures, and they have proven to be effective, but of course at the cost of a significant socioeconomic impact on the whole population. So it is essential to develop methods to support policymakers in taking decisions to mitigate the effects of the pandemic and to choose optimally, trying to reduce the impacts on the population, the control strategy. So we present a feedback control approach which makes joint use of a novel compartmental epidemiological model and a novel model predictive control approach. We employ a multi-regional framework, and the proposed approach is tested on real data of the Italian case study, showing its effectiveness. It has in keeping the number of threatened cases below a fixed threshold, while simultaneously minimizing the socio-economic impact of the required restriction periods. As a further development of the approach, of course, there are many possible future works, but we would like to consider age-differentiated control actions, so depending on the age of the population, and also, of course, including the vaccination, so at least a new compartment in this model, and also planning how investigating on how to plan the most effective way for the distribution of the vaccine, because how do we decide how can we decide giving the vaccination to people, what is more effective for the population and less strong from a socio-economical point of view. This can also be done with control. So thank you very much for your attention. Here, just want to mention that you will find all the references in the slides, so all of them. And also in the slides, here you have the web page, my web page, and the web page of the lab, where you can have access to the dashboard on COVID-19. Thank you so much for your attention, and I'll be happy to answer questions if there is some time.
Okay, Mariagrazia, thanks a lot for your very interesting talk. You can find the slides of the talk on the channel, okay? If you're not able to get them, please send me an email. I will send you the slides. So let's open, the question time. If you got any question, please unmute your mic and go ahead, or raise your hand. I will pass you the floor. Any question? Even curiosities or alike? I don't see any raised hands. I got a couple of questions, but before my question, please go ahead. If you got even curiosity, please. Okay, two questions. The first one is related to the model that I think it's, very detailed with respect to other models that I was able to analyze over, the last year. Majority of them are more, let's say, more simple than yours, take into account less parameters, but even dynamics. So my first question is related to this. Do you think your model is could be simplified, or what you put inside is what you need? This is my very first question. The second one is much more from computer science, software engineering. I really believe that your tool could be fundamental for decision makers, but I guess also that very likely decision makers do not have maybe enough understanding about the model. So maybe they need to be, let's say, supported using maybe some more simple tool with some, let's say, even human computer interface that could be more, let's say, easier to use, could be more intuitive, let's say, with respect to, the management of many different mathematical parameters. Okay, so these are my question, please.
Okay, regarding the first question, so the model, actually, our model is even simpler than other models in the related literature. So it is true that it is a model for regions, and of course in Italy, if you have 20 regions, then you have to have 20, let's say, submodels. And for each submodel, we consider 8 compartments. So 20 multiplied by 8, then it's easy to get the result. But actually, these 8 compartments are still smaller than in other models. Of course, you can still, if you want, you can obviously make it more simple. For example, by putting together some regions that are, let's say, homogeneous. I don't know, Molise and Abruzzo, or Piedmont and Lombardy, things like that. And also you can put together some compartments, which is what we did actually already. So you can decide to, let's say, have a higher point of view. That is always possible from a modeling point of view, but of course at the cost of accuracy. So the problem is finding a good balance between accuracy and detail, because of course we want to be accurate. Of course, if we consider everything as just one category, then we have perfect accuracy but no detail regarding the information on the different compartments. So it's always, with modeling, it's always a matter of balance. And of course, since these are models that can be run at least for one day, because we have information every day, it's not so important to have a model that is too simple, because again, we have one day at least to do all the simulations. Of course, when we will get data from the Protezione Civile every hour, which would be fantastic from me, from the, let's say, an engineer point of view, then we can think of simplifying the model. But unfortunately, I don't think this will happen, at least not in Italy, maybe in some other countries that are more precise, like, I don't know, China or other countries. So this is my first answer. The other question, can you remind me again? Because
yeah, it was about the tools.
Yes, the tools for the decision
which kind
makers.
of tools you can devise in order, to facilitate.
The tools for the decision maker. All this information that I gave you about the model can be completely transparent to the decision maker. I mean, the decision maker does not need to know how we define epsilon, how we define gamma, beta, blah, 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 whatever. All the data that we get from Google, he or she doesn't need to see this. What he needs to decide is simply what kind of control actions he wants to enforce and how. So I imagine, and this can be done very easily, a simple dashboard where the decision maker, the governor, or even the prime minister, can simply move a little bullet and decide, first of all, what kind of policy do I want? Do I want a policy that is the same for all the regions or not? Because this is a decision, and that's a political decision. It's not a decision that I can take or anybody else can take. So it's a decision at a political level. If I'm a governor of the region, do I want to apply the same condition with all the other for the other regions that have borders with me or not? This is also a political decision. And then regarding mobility, again, if I have selected my categories where I take the decision, so for example, shops, recreation, so I don't know, theaters, and then workplaces and transport, the decision maker can take these decisions by himself, just having this bullet where he can choose, I don't know, high level of control, medium, and so on. And then the whole system, the point is that this whole system can run, let's say, backwise, and then you can get the results. And the nice thing is that you can get the results in advance, so it can give you a forecast of what will happen, not only in terms of results, of course, hospital beds, situation for the population and so on, people that die and so on, but also in terms on how severe will be the control on the population. And this is what Paolo shows at some point, because I can be very precise and I can do fantastic forecasts, but I cannot maybe ask my population to change behavior every day like crazy. So one day I stay at home, the day after I go everywhere, then the day after again. This is, what we say in Italy, what color are we today? Every day that we get up, because we don't know. And of course, this is ridiculous. This cannot be applied. So it's again a matter of putting together engineering, let's say, and science with people. We are social animals and we cannot be controlled clearly like robots. So there has to be a balance between this. And again, this is a political issue. It's not something that as engineers we can decide. We can give the tools to the decision makers, to the politicians that can make informed decisions thanks to our tools. And I think this is mainly the message of this talk.
Okay, thank you very much. If we don't have any other question, we can close our lecture time. So thanks a lot, Mariagrazia, for your wonderful talk.
Thank you, Giancarlo.
See you next week, March 5. We will have a completely different topic. It is a topic related to real-time wireless systems. It will be given by Francesco Restuccia, who is with Northeastern University of Boston, and see you next week. Okay.
Can I just mention one last thing?
Yeah.
Sorry.
Yeah. Please,
here if you see my screen, here you have the website of the conference that we are having in Bari. And again, I remind you that the 1st of March, but some small extension is possible, is the deadline for presentation only paper. So you find all the information here on this website. So please come to Bari. It's a wonderful place, and we can continue talking and discussing about COVID-19, hoping that it will be just a past nightmare. Thank you so much again, Giancarlo.
Oh, great. So please submit something, because we already submitted. So we will see in Bari. Okay. So thanks a lot and see you next week. Bye.
Thank you. Bye-bye.